With the basic differential equation dp dt equals k times p, the positive number k represents the birth rate minus the death rate per individual per unit time. In reality, the natural environment has a limited number of resources, such as food and space, to sustain life. There's a point where life is unsustainable. Only a maximum population capital M can be accommodated. This number is called the limiting population or the carrying capacity. If the population is below M, it keeps increasing until it reaches M and it stays flat. If the population is above M, then it needs to be decreasing until it reaches M and it then stays flat. Thus, M is called the limiting population. P is small, then the population behaves as if it is with the basic exponential model. dp over dt is approximately kp, but as p approaches m, the population levels off, so the rate of change dp over dt is approximately 0. We can see from the graph because as p approaches m, the slope becomes more horizontal, meaning dp over dt is 0. We are interested in the relationship between the quantity k, which is dp over dt over p, and the population itself. Specifically, we want to know what happened to k if p approaches 0, and what happened to k as p approaches m. Now for the small p, that means p approaches 0. We see that dp dt is approximately kp, and as p approaches m, we saw that dp dt approaches 0. In the logistic model, the relative growth rate dp over dt over p, or k, decreases linearly to 0 as p approaches m. And so we can summarize this in the table. At p approaches 0, dp dt over p approaches k. And when p approaches m, dp dt over p approaches 0. This relationship can also be represented by a graph of p versus dp dt over p. As p approaches 0, the relative growth rate is k, and at p approaches m, the relative growth rate is 0. So the relationship is linear. This is the straight line. But this linear function has a slope of k over m. That is rise over run from the graph, and the initial value is k. And so the equation of the relative growth rate dp dt over p is k, the initial value, minus the slope k over m times the variable p. And so if we factor out k, we will have k times 1 minus p over m. If we isolate dp dt, we have kp times the quantity 1 minus p over m. This equation was first proposed as a model of population growth by the Belgian mathematician P.F. Hurst in 1830s. Observe that the constant function p of t equals 0 and p of t equals m are solutions of the logistic differential equation, because if p equals 0 and p equals m, then p stays that way. These constant solutions are called the equilibrium solution. So the equilibrium solution occurs when dp over dt equals 0.